All right, so let's get started. So welcome to another session of algebra geometry seminar. And today we are happy to have Zhang Ziwei to talk about tropical linear series and their applications.
Yes, thanks for the introductions. Yeah, so let us fix the notation first. So in this talk, so K will be an algebraically closed field with valuation from K to R bar, which is R union the infinity. So here we let the image if the valuation is infinity, if only if the element is 0. So we make such an extension to R bar. And this is complete with respect to the following norm. So this is our assumptions, and R will be the valuation ring. And K will be the residue field. So we use this notation throughout the talks. So so first our goal is to attach a smooth quadratic curve, a metric graph. So suppose X is a smooth quadratic curve over K, then we want to attach a metric graph to X through some degeneration, semi-stable degeneration of X. So first, let us define what is the semi-stable degeneration of X. So we say yeah, okay, so let me talk about this first. Originally I want to talk about this several minutes later. Yeah. So roughly speaking, so for each smooth quadratic curve with a semi-stable degenerations, we can attach a metric graph gamma. So we have the X and we have a gamma. And we have the tropicalization map. So we have two different tropicalization maps. So the first one is from the divisor of D to divisor on this metric graph. And we also have the tropicalization map from the non-zero rational functions to the piecewise linear function with integral slopes on this metric graph. So this tropical linear series is something similar to the tropicalization of algebraic series. So if we have a divisor in this metric graph, then we can consider the complete linear series associated to this divisor on the graph. And if we have a lift of the divisor D to the curve X, then usually the tropicalization map is not surjective. So it becomes a problem. So which tropicals are modular inside this R of D is coming from the tropicalization of the algebraic linear series. And such a question is important if we try to give some tropical proof of some questions on algebraic curves. Yeah, because it is related to if we have some piecewise linear function on graph. So do we have some rational function which leaves this piecewise linear function? Such a question is essential in the application. Yeah, so we try to characterize which tropicals are modular actually comes from the tropicalization of linear series. Yeah. actually, the current state is that our definition is not equivalent to the tropicalization of linear series. It's slightly more general, but we intentionally do this because maybe I'll talk about this later. Yeah. So that's probably the goal of today's talk. And say X is a smooth projective curve over K. So we say a semi-stable, so regular. Semi-stable model of X over a spec R. So R is the variation ring. It's a regular proper flat Morbihan.
So typically should we like take K as for instance algebraic closure of the field of rational functions?
Yes, that but here actually our K is the we can assume that K is itself algebraically closed, but we can it's slightly different. If we like K to be the function field of the curve, then what we need to consider is the geometric general fiber, and I guess the theory is more or less the same, but that will cause more the theory more complicated. So for simplicity, we assume K itself is algebraically closed. Yeah. So yeah. So yeah. Let me highlight. So the curve X is the generic fiber of this family, but not the geometric generic fiber of this family. So that will be the difference if we put this assumption. And so this is flat, and the generic fiber is the given curve X, and the spatial fiber is reduced with at most nodal singularity. So the picture is like this. So yeah, actually this picture is for it's for this case, but we somehow we mix the two situations. So this is spec K, and our curve is the generic fiber of this family. So we have X2 spec R, and sorry, this is spec little K, and the spatial fiber is something like the stable curve. Yeah.
So do you also want each irreducible component to be smooth?
That will be so-called strongly regular semi-stable model. So here we allow self-intersection.
Okay.
And the resulting graph will be having a loop. If you require the model to be strong, then the dual graph will be loopless. Yeah. So here, yeah, the usual semi-stable degeneration will be strong, regular semi-stable model. And in this case, we require the fiber, each component of the fiber to be smooth. So in particular, we don't have self-intersection. But here we allow self-intersection. We only require the singularity to be at most nodal. Yeah, so we can, if we fix such a regular semi-stable model, then we can attach a metric graph in the following way. So this is called the metric dual graph gamma of the pair X and the semi-stable model. So this is defined in the following way. So first, the index, the vertex of the graph is the irreducible component. Of the spatial fiber. So each curve gives you a vertex, but not an edge. And so we have an edge. So we have an edge connecting two vertex. If only if this is definition, the corresponding irreducible component intersect. So this gives you a graph, but we claim that it is a metric graph. So we need to assign the length to each edge. So this is defined in the following way. So we assume that the singularity is at most nodal. So it means that so for each edge of gamma, it is given by a node in a spatial fiber, right? So at tau locally, it is defined by the following equation. So it's defined by something like xy equals to f, and the f is an element in the maximal ideal of the evaluation ring. So we know if we are considered nodal in a node in R2, so it's defined by xy equals to 0, right? So here we want to define this node in the family. So the best we can say is that this term is replaced by something which vanishing on the spatial fiber. So, but anyway, we have this statement. So at around each node, at tau locally, it is defined by something like this. Then we assign the length of eta to be the variation of f. So of course, we need to prove that this is independent of the choice. It is indeed the case. Is no matter which f you choose, it gives you the same variation. So now we have a metric graph attached to a semi-stable model of a curve. So the first story I want to talk about is that we have some spatializing map which maps a divisor on the curves to the divisor on this metric graph. And they have some, we can compare them. To be specific, we can claim that the rank in here is larger than the rank here. Yeah, so that's the our first goal. And such a statement is very useful when we try to prove some theory on the algebraic curve, which involves divisors on curves, such as the Briones theory and other theory. So so we say that there's a spatializing map from between the divisor groups. So this is defined in the following way. So we need only to specify the image of each point of the graph, right? And then you just extend the map linearly. You get the map between group. So if we have a P in X, so it's like the it's like it's a point of the curve, but it's also the point of the generic fiber of this family. So after you take the Zariski closure of the point, it becomes a curve in this family. So we can take the closure map, which is closure P. Then this is the Cartier divisor on the family, right? Because we have these regular assumptions. Then we map this further to the following divisor on the graph. So V go through every vertex of gamma, and the coefficient will be this Cartier divisor intersect with the irreducible component given by the vertex V, and you sum over everything over V. So this will give you a map from a point to an effective divisor on the graph, and you extend everything linearly. That gives you the spatializing map of between the divisor group of a curve and its skeleton. So now of course, we can imagine that the divisor and its spatialization, we can compare them in some way. It is actually the content of the following lemma. So,
sorry, could you ask, what is CV?
CV. So, so we say that each vertex of the metric dual graph is the irreducible component of the spatial fiber. So if you have a V here, it is actually given by a irreducible component of this spatial fiber. So CV is this irreducible component.
So the intersection. So this is the intersection number.
Yeah, exactly.
So
because this is a Cartier divisor, so you can intersect it with this one. Yeah.
So a tropical divisor, is it by definition just so Z Z module generated by V?
Yes, free abelian group generated by points.
Just the V, right? So the vertex of gamma.
Because it's a metric graph, so the divisor group you allow the point to be any point. You can so if you have for example, you have a loop. This is also a divisor. Yeah.
So it's R vector space generated by vertices of gamma.
R vectors. You mean which vector space?
R vector space just generated by, you take a V of gamma as basis, and then
a V of gamma as basis, and what?
And you take the R spin of this.
R spin, but this is the abelian group.
So yeah, so a vector space is in particular a abelian group. So
or let me write out directly. So this is just the finite formal finite sum of such things. Yeah.
Then V. What is V in the in your?
This is a vertex
of little V, because in the sum here you have sum over some coefficient times V, but here your V is in the vertex of.
Yes, so it's the coefficient ahead of the point.
But then there are two things different. So Pi and V, they live in different things. So
the vertex is also a point on the metric graph.
So you only consider.
So a general divisor may not support it on the set of vertex, but the image of this spatializing map is supported on the vertex.
Okay.
But in general, you do have divisors which is not supported on the set of vertex.
Yeah. Okay, and these AI are real numbers or
integer.
Okay, and it's a finite sum.
Yes. It is sigma. Yeah.
AI are okay, so integers.
Yeah.
Okay, thank you.
Yeah. So so we have this spatializing map, and the spatializing lemma state that actually let's say this spatializing map is called rho. So the spatializing lemma assert that if you spatialize some divisor on the curve and you consider the rank, which will be defined later, then it is greater or equal to the rank of the divisor on the curve. So this is just the dimension of the complete linear series, which is also the something like this. So then we want to define what is the rank of the divisor on a metric graph. So this is the so-called Becker-Nernst rank. Yes. But no, actually, if we only talk about divisor group, then yes, we don't need a metric. But if we want to define linear equivalence on this divisor group, then we need the metric because it's given by the piecewise linear function with integral slope, and you take the divisor associated to this piecewise linear function. If you don't have metric, you cannot define the slope of piecewise linear function. Yeah, if we can still talk about linear equivalence on a general graph without metric, but in that case, divisor group means the formal sum of vertex. So you cannot take points on the edge. Because this in our situation is a metric graph, so we allow the divisor group to be the formal sum of points over it's any point on metric graph.
And what is R of rho of D?
You mean this one?
Oh no, so on the left-hand side of the inequality, so R of
I'm going to explain this right now. Yeah.
Sorry.
Yeah. So so this is the so-called Becker-Nernst rank of the divisors on a metric graph. So here, gamma is any finite metric graph, meaning that there's no edge with infinite length. And D is the divisors on this metric graph. So we define the rank of D to be the largest possible number such that for any effective divisor with degree equal to R, there exists a rational function. Okay, sorry, I forgot to define something before. So let me define very quickly something else. So so PL gamma, as we defined before, is the piecewise linear function. R linear, linear. R, yeah. From maybe let me say from gamma to actually we allow the value to be infinity with integral slope. Okay, so so for any such function, we can attach a divisor to this piecewise linear function. This is defined in the following way. So this is the sum of every point P, and the coefficient is the incoming degree of P or of F at P, and you sum over P. So here the incoming degree is just the sum of every incoming slopes of F at P. So for example, if you have a piecewise linear function like like this. So here you have slope 0, you have slope 1. Then at here, the incoming slope here is 0. The incoming slope here is -1. So you get a -1 here. So also we define the complete linear series associated to gamma to be the collections of every piecewise linear function, such that D plus D of F is an effective divisor. So you should really think about piecewise linear function as the rational functions on the graph. And this D is just the analog of the complete linear series associated to D. Yeah. So so here,
so could I also ask some clarification? So by piecewise linear, do you mean that so on each of the edge, the slope is constant, or
no, you can bend
okay,
in the middle of the edge. So you can
and incoming just means that you take the smaller.
yes, because usually a metric graph you don't have the direction. Right?
Yes.
But if you pick a point, you do have the well-defined notion of incoming. So
then if the point is on the edge,
you also you're trying to talk about this situation, right?
yes.
The notion of incoming is still well defined, right? So you have this. So there are 4 slopes to sum over. So yeah, you move the function from outside the point toward the point, and you get a well-defined slope.
Okay, so as long as your point is on the vertex, then all the adjacent edges are incoming.
Yes. So for a general point, you only have 2 slopes to sum over, right?
Yes.
Because a general point is of valence 2, so you have two slopes. So if the function is linear at the point, then the 2 incoming slope canceled, so you don't have any divisor there.
Why does the 2 slope cancel?
Yeah, because if you have a linear function and you have a p here,
yes.
So let's say it's slope 1. So so on a graph you have 2 edges, right? I mean, you have these edges and this edge to this point. And if you choose this direction, then you actually get slope 1. But if you choose this incoming direction, the slope becomes -1, right? Yeah, so you move point from here toward x, then the value is decreasing. Yeah. So that's the definition of incoming slope. You start from some point outside the point and move toward p,
okay.
and you get a slope. So in particular, if the function is linear at p, you get nothing. But yeah, if it's actually of valence greater than 2, then it becomes complicated. I mean, if you want to check this, the coefficient here is actually 0 or not, there's no, for example, it makes no sense to talk about the function is linear at this point. It makes no sense, right? So you need to check the sum of every incoming slope. Yeah. So yeah, it takes too long. So so let's go back to the definition of the Beck-Hennen rank. So gamma is a finite metric graph, and D is any divisor on this graph. So the Beck-Hennen rank of this divisor is the largest possible number R, such that for every effective divisor with degree equal to R, we have some piecewise linear function in the complete linear series of D, such that D plus D F minus E is effective. So in other words, you can move the divisor D within its linear equivalent class to cover the effective divisor D, and you must cover every effective divisor of degree R. So the largest such possible number is called the Beck-Hennen rank of R. So one can check that this definition, if you use this definition, it actually gives you the definition of D when D is a divisor on the curve. So this is just another definition for the rank of a divisor. But this divisor can be generalized to a graph. So that's the back-end rank. So the spatializing map here asserts that if you spatialize some divisor from a curve, then the resulting divisor will have larger rank in general. But it is always larger. It cannot be smaller. So so next we want to talk a little bit about how to use this spatializing lemma to give a tropical proof of the Briones' theory. So we will not talk about many details, just a sketch, because our topic today is tropical linear series, but not Briones' theory. So so let us recall what is the Briones' theory. So probably it is you already know, but let me recall it briefly. So the Briones' theory state the following. So we let so X is a smooth projective curve, and we assume it is general in some sense. And let WRD X to be some subscheme inside the Picard scheme of X. So the degree D component. So this notation is the Picard scheme of the curve D. So it's the linear equivalent class of degree D divisor, and there's a scheme structure on such a group. And if you fix a degree, then you get a component. So this is a subscheme of this component of Picard scheme, and the Briones' theory is about the dimension of this subscheme, and this subscheme is defined to be the divisor class such that degree D is D, and the rank of D is greater or equal to R. So this is a subscheme of the Picard scheme, and so from some argument, we can write down the expected dimension of this subscheme, which is the so-called Briones number. It's the genus of a curve seesaw is X, sorry, minus R plus 1 times the GC. So this is so-called the Briones number of this associated to these parameters R and D, and it is the expected dimension of the subscheme. So now the conclusion is, if X is general enough, then first, if the Briones number is negative, then WRD is empty. And the second is that if the Briones number is non-negative, then the dimension of this WRD is the minima of rho and the G. So if G is smaller than rho, then in that case, we can use Riemann-Roch to argue that this subscheme is actually equal to the whole Picard scheme, so which has dimension G. So if G is smaller, then we don't have any interesting thing to prove. So the actual challenging case is that if the Briones number is smaller than G, so how can you show that the subscheme actually has dimension equal to rho? So it is standard that to prove Briones' theory, actually you only need to demonstrate one Briones general curve. So because you can show that this is kind of an open property, so you need to write out one curve such that this statement is satisfied. You don't need to check take any general curve. You only need to demonstrate one curve. But so here is the so you know Brier-Nusselt general curves consist of some open dense set in the modular space, but it is not easy to write down any of them. So yeah, that's the point, to write down a single Brier-Nusselt curve. So the tropical proof is a process to produce a Brier-Nusselt curve. So you start with some spatial curve, spatial graph, and this graph satisfies some tropical Brier-Nusselt theory. And then you take the graph with a semi-stable model, whose geometric graph is this graph. Then you can show that this curve is actually Brier-Nusselt general. So let me say something more about this. So
sorry, could I ask some elementary questions? So is the vector space big RD finite dimensional?
You mean a switch
vector
space?
Big RD. So I think
you mean as R vector space?
Yes, because I'm not sure whether I understand correctly. So RD should be the tropical analogs of linear series of D, or
so this is not a finite dimensional vector space as R vector space. But for example, you can consider an interval and the D is like 1. You have coefficient 1 here. Then you have many divisors in this RD, many piecewise linear function in this RD. So first you have this constant function, right? And then you have this function. So this function, you have a -1 here, but you have a 1 here. So they cancel out to give you 0, and you have 1 here. So it lives in RD. And you also have, you can make the band locus to be any point in the interval. So as a R vector space, it is not finitely generated.
And should we understand RD as a tropical version of?
Yes, that's the point. So actually, you can define the tropical operations on R of D. So tropical operation, this should be the content of the 20 minutes later. Okay, so you can define the scalar multiplication to be the usual sum. I mean, this is the usual sum. This is the tropical multiplication, and the tropical sum to be the minima of the C1 and the C2. So you can check that these are all piecewise linear functions in R of D if C1 and C2 are in R of D. So you are right. In this sense, R of D is a finitely generated tropical module. You can find a finite set of piecewise linear function, and every other piecewise linear function are generated by them through tropical operations. Yeah. So that's the. I mean, it almost makes no sense to consider this set or any tropical submodular as R vector space.
So small RD should be understood as the minimal number of function that you can generate big RD in the.
I think that they are not the same. You try to say this is the
then
size of the minimal generating set.
Yes,
but actually no.
Then how can we understand small RD?
Yeah, that's something I do not know. Yeah, maybe there are some insight for this definition, but now the best I can say is that because for divisor on curves, you can define the rank to be this number.
Yes.
And this number also makes sense when the divisor is a divisor on graph. So you just copy the definition and you get a definition for ranks. Actually, there are some other rank. For example, you can talk about I mean, TLS stands for tropical linear series. This so I guess this is closer to what you just said. I mean, the size of minima generating set.
Okay.
But in general, there are many ranks you can define for devices on a graph. And here we talk about the back-end rank, which is defined in this way.
Okay.
Yeah. So okay, so let me give the so I will not talk about the detail of the proof. Let me just give the sketch. So what is proved by the authors? I mean, you can check the following paper. So they actually find a brilliantness general finite metric graph. So there is a finite metric graph such that the following things are satisfied. So first, so we can still talk about the brilliantness number associated to I mean, given a graph, we can talk about the brilliantness number, right? So the only thing you want to so this is a brilliantness number. So if X is a graph, you just need to replace the graph, the genus of the curve by the genus of the graph. So it's defined to be the let me think. So it's the it's a number of edges minus the number of vertex plus 1. So you have you can define the brilliantness number for a graph, and if the brilliantness number is negative, then they assert that there is no effective divisor such that degree E is D, and the rank of E is greater or equal to R. So in other words, it says that WRD is empty here. So the second one, which might be a little bit different from the second item there, it says that there is a spatial point on the graph such that if we consider the following divisor, then this is not contained in any complete linear system with degree D equal to D and RD greater or equal to R. So this is just all the effective divisor, which is linearly equivalent to D. So they are linearly equivalent if the difference is given by a piecewise linear function. So this is, we can think of this theory as the tropical version of the brilliantness theory. And so what I did is that then you can, then it's a basic fact that any finite metric graph is the dual metric graph of some smooth projective curve over some algebraic closed valued field together with the regular semi-stable model. So you take X to be such a curve, and you apply the spatializing lemma. Or for some k, I only for some k. I don't. I think if the statement is for any k, then it's not true. I only assert that for some complete validity field, and some smooth projective curve over k, and some semi-stable model of X, the dual metric graph is this given finite metric graph. So you choose this smooth projective curve over k, then you plus the spatializing lemma, you can show that X is Briones-Zer general. So that's the very sketchy proof of what I did in the paper. So
in the theorem, what is rho?
You mean which?
The theorem.
You mean that one?
Yeah.
The Briones-Zer number.
But there's only graph. There's no curve.
Say again.
There's only gammas, so there's no curve in the theorem.
It is gamma, so I just said it. So you just replace G by of gamma.
Okay.
So you have a well-defined Briones-Zer number. Yeah, then the G of gamma is defined in this way. Yeah.
Thank you. Sorry. Yeah.
Okay. So yeah. So of course the crucial point is to prove this tropical version of Briones-Zer theory. Then it's a purely combinatorial problems, but it's by no means easy. But you need to. The good news is that you can apply many combinatorial argument to find such a curve. So it's actually some chain of loop. So this is your gamma. So the number of loops is your genus G, and you need to control the upper length and the lower length. So if the ratio of the upper length and the lower length are in some general range, then you can argue that it is the Briones-Zer metric graph. So if you take an arbitrary chain of loop, it may not be Briones-Zer general. So you need to make some assumptions on the length of the metric graph. So that's
yeah. So what would be the simplest gamma which satisfies the conclusion of the theorem?
Yeah, that's what I say is it's a chain of loop. Yeah.
Okay.
So I'm not sure whether they have
one loop is okay, or
one loop.
Yes.
No, you
how many loops do you need?
First you need to fix G, right? So you are talking about G equals to 1 case. If you fix G, then the number of loops must be equal to this G, because in that case, the genus of a graph is equal to the number of loops. So when you discuss Briones-Zer theory, you need to fix G, and the chain of loop will be a chain of G many loops. Yeah. So like I said, if you take any chain of loops with G many loops, then it may not be Briones-Zer general. You need to control the length of each loops. I mean, for each loop, you have the upper length and the lower length. You need to control this length. Yeah.
Okay, thank you.
So yeah, so that's why this Briones-Zer metric graph is not very simple. You actually need to do something to argue that it is Briones-Zer general. So anyway, the point is that you can translate the Briones-Zer theory into some purely combinatorial problem through this metric dual graph and the spatializing lemma, which relies on the divisor theory on graphs. So roughly speaking, you have two processes. So first, you need to tropicalize the curve into some finite metric graph, and you need to study the divisor theory on the graph. And then you need to know how to compare the divisor from the curve to its spatialization. Then you will encounter some tropical version of your original problem. So what I'm going to talk next is that this approach can be applied to problems concerning non-complete tropical linear series. So the problem of Brunner series and is about divisor, right? So the specializing lemma is also about the rank of the divisor. But there are some problems for algebraic curves which involves non-complete linear series. So in the next 30 minutes, I want to say that we have a way to we have a similar picture, a similar tropical approach to such a problem.
And is it possible to prove that conversely, if you start with a Brunner general smooth projective curve, and you take
any skeleton of X.
So you obtain a finite metric graph, and the finite metric graph satisfy the.
I don't think so. You only have one direction because the specializing map says that the rank will be larger.
I say inequality instead.
Yeah, for example, the first item says that something is empty, but if the range becomes larger, then it might appear something else. So this kind of argument only works in one direction. Yeah. Later we will see the same thing happens for tropical linear series. If you have something, you have some linearly independent set. If you have some linearly dependent set, you will get some tropically dependent set after tropicalization. But if you start with linearly independent set, then we don't know whether the tropicalization is independent. So you always have one direction only.
Okay, thank you.
Yeah. So oh yes. So it's the so you run through every vertex of gamma, which is the balance of -2, I guess, and times v. So so valence means the number of edges. Emitting from v. Therefore, for example, if you have a loops, then the canonical divisor is 0, right? And if you have a tripart, it is. Am I correct? Yeah, but anyway, yes, there's a well-defined notion of canonical divisor for graphs. Yeah, and there's also a tropical Riemann-Roch for graphs. Yeah. So the tropical Riemann-Roch is also stated through the Beck-Nernst rank here. So yeah.
And if you take a piecewise linear function on gamma and look at the divisor associated to it, and is the degree also equal to 0?
Yes. Provided the graph is connected, yeah. But we always talk about the connected finite metric graph, yeah. So this is this set should be considered as the principal divisor on gamma. So the linear equivalence relation is defined by dVF.
And if D is an effective divisor on gamma, is small rd equal to the degree of D?
No. You want to say if this is effective, then
no, if yes.
No, it's not. Yeah. So it's least rank is for example, if we have a divisors on curve, so least rank is the dimensions of the complete linear series -1. So we do have some relation of the rank and the degree, which is the Riemann-Roch, the content of a Riemann-Roch. But in general, they are different, right? Yeah, so here we have we are in the same situation. We have the Beck-Nerney rank and we have the degree of the divisor. They are associated by the so-called Riemann-Roch for graphs. But in general, they are different. Yeah. I guess, yeah, you can easily write down the statement of Riemann-Roch. They are identical. You just replace rank by the Beck-Nerney rank here. And yeah, so maybe I'll skip more detail. So because I want to talk about how to tropicalize the rational functions on the given curve, so I need to introduce some notations in Berkovich geometry, but I'm not sure it is worth doing. But so let's say X is a smooth projective curve over a complete evaluated field K, which is algebraically closed. Then so here we want to define the tropicalization maps in a more general setting, which makes use of the Berkovich geometry. So the Berkovich identification is, as a set, is the following set. So it's the set of scheme point of X with evaluation from the residue field to R bar, such that we have the following commutative diagram. Right, so it's a collection of different variations on different residue field. So in particular, we can realize the K point of this curve as a subset of this Berkovich identification. So each K point of the curve X gives you a discrete variations on the function field of the curve. And the function field of the curve X is the residue field of the generic point of X. So that gives you a point in the Berkovich identification. So we have this nature inclusion. And so let me skip some details. So let's say we have a regular semi-stable model. So this will give you a metric dual graph, as we said in the beginning. So we also have a nature inclusion from this metric graph to the Berkovich identification. So this requires some explanation, but so roughly speaking, let me skip some of the details. So for example, if you have a vertex of V, then you want to attach some variation to this vertex V. So how can you do that? So V is associated to some irreducible component of the spatial fiber, right? So you want to define a variation from the function field of X. Maybe we don't need this, to R bar. Then you can define in the following way. So if you have rational functions on the curve X, then you send this to the valuation of some element A, such that A satisfies the following. So A is an element, non-zero element of K, such that AF is regular and non-vanishing at the generic point of this component. Right. Of course, you need to check this is again independent of the choice of A. But yeah, indeed it is a case. Then you can attach if vertex V to evaluations on the function field. So it actually commute with the original valuation here. So it is a point in the Berkovich identification. And also, if you have a vertex, no, I mean, if you have an edge in the vertex of the geometric graph, then this corresponds to some node of the spatial fiber, right? So it is locally defined by some equation of this form, as we mentioned before. Then, so the point in this edge correspond to some monomial valuations attached to the coordinate x, y here. So if you write down such an equation, then you have a coordinate on the total family here. And you can define a valuation, a monomial valuation in this manner. So you can easily verify that you can vary alpha and beta. And this is in a one-to-one correspondent to point on the edge. But anyway, the point is that if you have a point on the edge, you can attach a monomial valuations on the function field of the curve. So this embedding, for this embedding, all the residue field is the function field of the curve. Okay, so what is less obvious is the following thing. So there's there is a deformation retract from the identification to the skeleton X associated to a regular semi-stable model. So, and also this map induces a surjective map from the K point of X. So we have mentioned that this is naturally embedded to the identification. This is subject to the gamma. So now, what is the spatializing map of divisor? You can use this projection. So in short, we have the tropicalization map from the divisor on X to the divisor group of gamma. So this is the tropicalization map we have before. Sorry, they might not be the same because in this way, the image of this tropicalization map may not be supported on vertex, right? So, but it's also a tropicalization map, and it also satisfies the spatializing lemma. But you need to prove this. But the point, what is important for the next 20 minutes of talks is another tropicalization map, which is from the non-zero rational function to the piecewise linear function on gamma. So if you have this tropicalization map, then you can talk about the tropicalization of any tropical linear series, because a algebraic tropical linear series is just a linear subspace of this group. So this is defined in the following way. So if you have non-zero rational functions. So this will gives you a function which is defined by P sent to the variation of P at F. So we have mentioned that so gamma is embedded into the identification of X, and there are all variations on the function field of X. So fixed at P, you have a valuation P, then the value is just the this F. So it's not hard to see this actually gives you a piecewise linear function on gamma. So you can also check that this is a surjective map. So now we have a tropicalization map for non-zero rational functions. So so I want to talk about what can we do through such a tropicalization map. So we can use this tropicalization map to give a tropical proof of some theory concerning the non-complete tropical linear series. So let me say something about this. So okay, so let me mention some easy property of this tropicalization map. So it's not hard to check that if we have a set of non-zero rational functions, which is linearly dependent, then we have the following thing. So we have R many rational numbers such that the minima of A1 plus AI plus trop Fi, when you go through every possible I, is attained at least twice. So in other words, so let me draw some picture about this part. So in other words, your set of piecewise linear function is like you have, for example, you have this piecewise linear function. So this is the first one, and you have this one, and you have also these three functions. And at each point, sorry, I want to say this is yeah. So this is your arbitrary point P. So you consider a minima of this set of number. So they are at this. So this appears in this set at least twice. That is what the assertion is about. So the picture is like this. So yeah, when you consider the minima of this set, then each point you have two functions intersect at that point. So we have these easy propositions, and we.
So is the tropicalization map morphism or semi-ring?
Morphism of what?
Semi-ring. So you have so left-hand side is a ring.
Yes.
And the right-hand side is indoor with min and plus is semi.
First, this is true because of the property of valuation. And I think, but the problem is the sum, and
yeah, is it equal to the minimum?
Yes, I think so. Yeah, it's the.
Yeah, then the proposition follows from this, right?
You mean this proposition follows from this one?
Yes.
I guess you also need to make use of the property of the valuation. For example, if you have a I mean, if you have a sum of functions and you take the valuations, so if you know the valuation is infinity, then you know what is what?
Sorry.
I mean, let me explain the essential argument for this proposition. So if you have n many functions and you know the sum has valuation infinity, which means that their sum is 0. You have a linear combination of this one. Then you must have that the minima of the valuation of the monomial. Maybe here this is not. If you consider this set of number, the minima is attained at least twice. If each term you have different valuation, then the valuation of the sum is just that minima. So to have this equality, you must have that the minima is attained at least twice. Yeah, it's just the direct result of the property of the valuation. So this proposition comes from this property of valuations. Yeah, but you're also right because it respect to some operation. For example, if you consider the tropicalization of the multiplication, then it's just a it's just a usual sum on these two piecewise linear functions. If you consider the sum of the tropicalization of the sum, then it becomes a tropical sum of the corresponding piecewise linear function. But I guess this is the best you can say. Yeah. So and also the image of this map is a tropical module. Yeah. So yeah, you need to. Yeah, I think it's nothing else I can say. Yeah. So anyway, from this proposition, it's reasonable to define the following notion. So we say a set of piecewise linear function on gamma is tropically dependent if there exists are many functions, are many real numbers such that the minima of this set of number is attained at least twice. For every p. So the picture is the picture here. So plus that you can move, you can change, you can move by a constant. Yeah. So let me move to the how can we use the tropical independence, the notion of tropical independence to prove the maxima rank theory? And finally, maybe let me make some comment on the tropical linear series and the definition of it. So so let's recall what is the maxima rank conjecture, which is now a theory. So this is proved by Eric Larson in a series of papers in 2017. So the statement is the following. So suppose
I think Larson with R instead of W.
yeah. Sorry. So suppose X is in general. For example, Brianna's a general, then given a pair of number, we let V to be to be a general linear series. Such that the degree of this divisor D is little d, and the dimension of this linear series is R plus 1. So of course, you need to make sense of what does it mean by general linear series, but you can actually do so. Yeah, you want to make sure that you have a irreducible moduli space which parameterizes Breuer's general curve with a linear series satisfy this property. This actually such a moduli space. So general just means it is outside a Zariski proper Zariski closed set. So the statement is the following. So then we have the nature map from symmetric power of V to the complete linear series of D, right? There's a nature map. And the assertions is that this is either injective or surjective. So in other words, the image has the maximum possible rank. So similar to the Breuer theory, you only need to demonstrate one Breuer general curve with one linear series which satisfies this property. So we can try to mimic the tropical approach in the Breuer theory. So we can just try to find some special metric graph and a tropical linear series on that graph which satisfy this maximum rank conjecture. And then we try to lift the graph and leave the tropical linear series. Then we will demonstrate one of such things. So that's roughly the idea. So let me state something more about this. So so actually, originally I want to explain something about the sketch or proof of this maximum rank conjecture. I mean, using the tropical independency we just defined. So let me skip this part because I want to talk about what we did tropical linear series. So
so is the proof simpler using a tropical curve to prove a maximal rank conjecture?
Say again?
Is the proof simpler, or because original proof is like 100 pages and
yeah, consists of 6 many papers, and some of them are not even published. Yeah. So the original proof is not a tropical proof, yes. But there is some. But some of the essential step is a combinatorial argument. So I would say some of the essential idea already appears in Eric Larson's proof. Mm-hmm. Yeah, but here we want a purely combinatorial, a tropical proof of the maximum rank conjecture.
So is the proof already complete or just?
I think the community accept that it's a complete proof. Yeah, but if I recall correctly, not every of his paper is published. Yeah. So, but if you check the wiki page, now it says it's maximum rank theory.
Yeah. But I mean the tropical proof, is it complete?
No. The tropical proof, which is a work of Saint-Payne and David Jensen, they only prove that if the power is smaller or equal to 2, then we can actually find such a spatial graph. This is again the chain of loop, but with bridge. Yeah. So yeah, they always play with similar graphs like this. Yeah, and you have some special devices which supported on some set like so. And the crucial thing is that you want to write out a set of piecewise linear function. Say you have to PL gamma. You want to check that this set is tropically independent, which means they are not tropically dependent. And you also want to check that this is also tropically independent. So if you can find such a set of functions, then you can prove that if M is equal to 2, then you have maximum rank conjecture. So the crucial part is to find such a set of piecewise linear functions, and they only managed to prove the existence of such a thing when M is equal to 2.
I see. So when M is arbitrary, then you need so M terms of some is.
Yes. This actually corresponds to the like you asked before. It's a multiplication of Fi times Fj. So the image is generated as a vector space by this element. When you tropicalize, you get this piecewise linear function. If you can check this is independent, then this set will also be independent. So this will tell you the image, the map is injective. So so it is surprisingly complicated when M is greater or equal to 3. Yes. So again, it's a purely combinatorial problem, and you only want to check something like this. You are allowed to add some constant to each piecewise linear function, and you want to see whether it is possible to move them to satisfy this property. But it's not easy. So they try to give an algorithm to check whether a given set of piecewise linear function is tropically independent or not. But I think it's not so successful. They can only address some special case. Yeah. So yeah. But anyway, they can use the notion of tropical independence to give the tropical proof for maximum rank conjecture when the power is smaller. Yeah. They have the complete proof for when M is equal to 2, partial proof when M is equal to 3, and when M is equal to 4, it's completely unknown. So yeah, they don't have such a proof for that. It's because this kind of problem is doable when there are only 2 terms. Yeah. So so maybe let me because I'm running out of time, so let me mention something. So as I said, so the crucial point of the tropical proof of the maximum rank conjecture, you want to leave a set of piecewise linear function to rational functions on the original curve. So the question is, so if we have the tropicals are modular, so when do we have this sigma is actually the tropicalization of some linear series where V is some so of course, not every tropical submodular of RFD is the tropicalization of tropical linear series. There are some abstraction. So this motivates the following definition. So this is the tropical linear series. So gamma is the, let gamma be an arbitrary finite metric graph. And sigma is a finitely generated tropical module, which means it's closed under the tropical operations we defined above before. So we said that sigma is a tropical linear series of rank R if the following three things are satisfied. So the first thing is that the back-entering rank of this sigma is greater or equal to R. So so it means that for any effective divisor with degree R, you can find a function in sigma such that D plus div F minus that effective divisor is effective. So, I mean, it's just the same statement when we consider the back-end rank for divisor. So the first condition is that the rank is greater or equal to R. And the second one is any collections of R plus 2 functions in sigma. So they are tropically dependent, which means that this size cannot be too large. So the third one is that any R functions are contained in a tropical linear series, sigma prime in sigma of rank R minus 1. So it's an inductive definition. So so conceptually, this is very similar to the tropical submodular, which is the tropicalization of some tropical linear series. But actually, this is slightly more general. So it becomes a problem that, so because I'm a little bit over time, so let me state what we get and the sum of the open problems. So so what we can say is that, okay. So when gamma is an interval, so we can characterize every sigma of rank 1. So this is done by myself and several other people. You might think that the metric graph interval is too simple to compare to an arbitrary metric graph. But actually, when we discuss properties of tropical linear series on any metric graph, you can restrict the tropical linear series to the subgraph, which is an interval. And in many cases, it is enough to determine some of the property of a series. So it's basic and important to study the tropical linear series on interval, and it is not yet completely understood. For example, we can for some technical reason we can only characterize every rank 1 tropical linear series on interval, and also when gamma is a loop, we can characterize the every tropical linear series of rank 1. And there are several other examples we can do, but let me say something about the ultimate conjecture. So we want to prove the following things. So so suppose sigma is a tropical submodular such that the Beckner rank condition is greater or equal to R. And there is a surjective tropical linear map from a tropical linear space. Let me explain later. Surjectively to R. Then it is actually a tropical linear series of rank R. So here, this is the tropical linear space of dimension R plus 1. So you should think of this as the tropicalization of usual linear space. But actually, it is not. Some of the tropical linear space is not realizable. But the point here is that the tropical linear space is in a one-to-one correspondence with the so-called variety matroid. So if we can prove such a conjecture, then it is nice because we have a similar picture of the algebraic case. So the algebraic series is just the image of a linear space, right? So here it's just a tropicalization of these pictures. So the tropical linear series should be something like the image of a tropical linear space, which is the which is a variety matroid. And also, if we can establish such a conjecture, then we can reveal some interplay between the algebraic linear series, tropical linear series, and the matroid theory. So that's our hope. But so far, we can only characterize some very simple case. But as I emphasize, these examples are basic, but they are like the most important cases. Yeah, I think I should stop here. Yeah, I have some other stuff to share. I'll stop here. Yeah.
Thank you very much for the very interesting talk. So are there any questions? Yes, Pedro.
So do you know this RD, the R, where it comes from, the notation? Is it related to these repartitions from the surge duality proof, or it does nothing to do with that?
You mean these are the or?
Yeah, RD. Yeah.
Yeah, or could you please explain again the conjecture? So
Okay. So this conjecture is about how to produce tropical linear series. And the way we produce the tropical linear series is that we start with a tropical linear space, which has the given dimension +1. And we consider the image of some tropical linear map. If the image happens to have Beckner rank greater or equal to R, then we claim that it is actually a tropical linear series. Yeah, that's the content of the conjecture. It's about how to produce a tropical linear series.
okay, so from some higher rank thing.
From higher rank thing, but this is I use this notation, but this should be this is actually something of dimension R. Yeah, for example, a tropical line is a two-dimensional tropical variety with so
What is lambda R plus 1?
It's a tropical linear space with dimension R plus 1. I haven't defined what is a tropical linear space, but yeah.
Okay.
But a tropical linear space of dimension R plus 1, you should think of it as something having dimension R. Yeah, because there's a linearity space. So this is actually lives in some free module R-bar2. And
our lambda 1, what is lambda 1?
Lambda 1 is the point. It's the it's like you have a point, and there's a one-dimensional tropical submodule generated by this F, which is the F plus this is one dimensional, right? But you should actually, but in this, this modular is in R bar to the n, which is one dimensional. But usually we want to consider the image of this set inside this quotient space. So in this space, it's actually of dimension 0. It's a point. Yeah. So that's a R+1 dimensional tropical variety. But actually, you should think of it as a R dimensional object. Yeah. So, for example, if you consider everything in this quotient space, then a tropical line is actually something like this, or you have some degenerate tropical line. If you consider a tropical line in a regional free modular, then it's a two-dimensional object. Yeah, that's why this notation you have a +1 here. Yeah.
Are there other questions?
This is any tropical linear map. Yeah, so we so the conjecture says that if we can find a tropical linear map phi from the tropical linear space, which is also a tropical modular, to sum to R of D, which is a tropical modular, and the image satisfies this condition. I mean, the Beckmann rank is greater or equal to 1. Then this image is going to be a tropical linear series of rank R. So this is something you want to find. Yeah, a tropical linear map from the tropical linear space. Yeah.
And where do we use the deformation retraction map?
You mean at the beginning, right? So we say that the duometric graph is naturally embedded in the Berkovich
Yes.
identifications. And we have this deformation retract.
Yes.
And this map actually gives you a projections from the K point, which is also naturally embedded into a Berkovich identification. And this map is surjective.
Yeah. Where do we use this?
It's used to define the tropicalization map between divisor group.
Do we really need this, or we can only use? Can we just use a valuation to define tropicalization? So namely, just get rid of Berkovich space.
You mean you want to define a map from this to the skeleton directly from the
So sorry. So this is what you say, that there are two tropicalization. This is not the one that you defined at the beginning.
I think that they are different because this tropicalization map, the result divisor can be something which is not supported on the vertex.
Where did you use the second tropicalization map?
Oh, yeah. I mean, you mean
this one?
By second, you mean this one?
Yeah. So
no, we don't need such a.
So we don't need Berkovich space.
Actually, yes. We still need. Sorry. Let me withdraw what I just said. We do need such a map because we want to leave the divisor on a graph. By leave, I mean so if you have the divisors on a graph, so a lift of a D is again a smooth projected curve over some complete evaluative fields, which is algebraic closed with some semi-stable model, such that the duometric graph is this gamma, and you have the divisor D,
which is the preimage of
such that the tropical. Let me write tropical. D is D if you stop here, then this can always be done. I mean, any divisor is the tropicalization of some divisor on the curves. But what do we mean by this? Is we need one more assumption. So the rank of the divisor on the curve is equal to the backend rank on the divisor of the divisor on graph. So the leaf is such a datum. We for example, if we want to I'm not 100% sure. In the tropical proof of the maxima, I'm not sure. Let me not say this.
Okay.
But anyway, you want to consider this leaf, and this trope is a trope here. Yeah, maybe let me replace this by trope. Yeah. So this kind of process is important. Yeah.
So are there more questions?
May I ask a question?
Yes.
Yeah.
About the definition of the tropical dependence, the linear dependence of the piecewise linear function. So why is it defined that way, as defined as the minimal, the least value is obtained twice? Why not define it just like usual, like it's equal to 0?
Because
It's
there's no
equal-
zero. There's no zero. So
It's all 0 because if the piecewise linear function is not a constant function, then you cannot have a usual linear combination such that is the constant function 0. So
It's not. I'm not saying use the usual linear combination. You use the tropical linear combination as what you write,
yes.
right? The minimum of AI
Oh,
plus.
you are saying that maybe we have something like
this is because the valuation sends 0 to infinity. So the only way to make sense of linear dependence is what Zhiwei wrote.
so. I guess what you want to say is that we can define a set of piecewise linear function in the following way. So there exists a set of real numbers such that this tropical linear combination is a 0 constant. Is that correct?
Yeah.
Yeah, but there's no 0, right? So valuation sends 0 to infinity. So it shouldn't be 0. It should be infinity. So
yeah.
the only thing that makes sense is what you wrote. So minimum attained twice.
I think this statement makes sense. So what?
But I think it's not the right notion of.
I mean, we can define something
Of course
like
you can
this.
define, but it will not be the.
It will not be the correct
Yeah.
dependency because, because of a property of the valuations.
So my question is why this is not correct. If you have a linear independent rational function on curve and you tropicalize, you will get something like this, right?
No, because tropicalization is you use valuation, right? So invariant dependence means that something equals 0, but if you tropicalize, it becomes something equals infinity, not equals to 0.
Yeah.
So this means that the one on the blackboard is not the correct notion of linear dependence.
Then what if we just change the 0 to infinity?
Then because then you rarely have anything that you rarely have any linear combination which is equal to infinity.
Oh, if you have just a linear dependent, I mean the actual linear dependent linear series coming from actual curve and you tropicalize, what will you get?
You mean independent, right?
Dependent.
Dependent. So
yeah. If this comes from actual curve, the tropicalization of actual curve, then what's the condition when you tropicalize such linear dependent thing?
So if you have a set of rational function which is linearly dependent,
and you tropicalize, won't you get something like that?
Is tropically dependent.
I'm asking, will it satisfy like a stronger condition, like something like the tropical linear combination will be equal to, I don't know, 0 or infinity or something like that? Not just the minimum value is obtained twice.
I don't think so.
Because on the originally is linear combination is equal to 0. That's the original series. And
Yes.
I recall you said when you tropicalize, that's actually a homomorphism semi-ring or something like that, right? So you will
Yes.
respect the scale multiplication and the sum. You will change the usual scale multiplication to the tropical scale multiplication, and you will change the usual sum to the tropical sum.
No, maybe writing again. So what I know is that if you tropicalize the multiplication, then it's the usual sum, not the tropical sum. And if you tropicalize the sum, the usual sum of rational functions, it gives you the tropical sum of.
Yes.
piecewise.
So if you write down, so the original series you have AI Fi plus An Fn is equal to 0, right? That's the original series.
Yes.
And when you tropicalize this equation, what will you get? You just tropicalize the both sides, and what will you get?
Yeah, it seems like it's the one you write down on the blackboard.
But you cannot tropicalize.
Because there's no 0 is not in the domain of definition of.
Yeah, it is not. Yeah.
Yeah.
So the tropicalized map is from non-zero rational function.
So right-hand side doesn't exist when you tropicalize. So this is why you have to define the way Zhiwei write down.
You need to analyze the property of valuation to get this statement. Yeah. I mean, I guess it doesn't make sense to talk about to tropicalize this equality. Yeah. Yeah. So anyway, the content of this proposition is that if you have a linear combinations, then the resulting piecewise linear function satisfy the definition appearing in the tropical dependencies. Yeah.
Okay, thank you.
So are there more questions? So if there's no more question, then next thanks Zhiwei again. Thank you very much. Yeah, so next week, same place, same time, we will have another seminar. So by Sasha Kuznetsova.